Continuing on, if your SA node stops, then your AV node will actually pick it up and become your new pacemaker. Your resting heart rate will be a little bit slower and such. If the AV node quits, well, you're in a world of problems now. Then the rest of the fibers might try, but they just can't cause the heart to beat fast enough to supply the brain with appropriate oxygen. And so then you would succumb to that. If caught early enough, an artificial pacemaker can be placed in an individual to fix that, to correct that situation. Looking at the muscle itself and thinking about its contraction cycle and such, you have to go back to what you learned when you did muscles in A&P1. You know that the sodium's on the outside of the membrane, the potassium's on the inside of the membrane, and that creates this charge difference, and we say that the cell is polarized. The cell membrane is polarized. And when you get a stimulus, when something happens, the sodium rushes in. And when the sodium rushes in, the charge changes, and we say that it is depolarized. Then the potassium rushes out, and we say it is repolarized. In the act of depolarization, that travels all the way through the muscle fibers, which causes the calcium to be released, which then the calcium attaches to the troponin, and you have the tropomyosin move, you have the ATP attach, you have the myosin bridge, you have the myosin swivel. Remember all of that? That's the actual contraction and such. And then you have the repolarization, and that stops. Then you have the period of time where everything is reset, that refractory period and such. So thinking of the heart, when you think of heart fibers and all, you've got conduction and you have contraction. And the SA node, the AV node, the bundle of His, the Purkinje fibers and such, those are the conducting myofibers or fibrils. And then the actual muscle cells themselves, the one that actually does the contracting, does the pumping, that's the contractile valve. Contractile fibers and all. Same arrangement, we mentioned that, thick and the thin, the actin and the myosin and such. The same result, muscles shortening in this contraction and such due to the myosin cross-bridging and swiveling, which ATP is necessary for that to occur, but to do that, to start that off, you have to have the depolarization. The SA node does that and such. So in a regular skeletal muscle, you have to create that thought in your frontal lobe. It has to travel down through your spinal cord, has to then leave and go out a motor neuron, has to then go to a synapses. Acetylcholine has to be released. It then acetylcholine has to attach to a receptor. That then causes a depolarization of the sarcolemma, which then travels across the surface and down through the muscle fibrils themselves, which then goes to the cisternae, which then goes to the SR, and calcium is released. Remember all of that and such? In the heart, it's a little more quick. It happens a little bit faster than that and such. So, same thing happens. The same thing happens. It all comes down to this release of calcium. The same thing is going to happen and such, but a little bit different, a few little differences and such. So we mentioned the speed that the SA node contracts and such. We mentioned all of that. So, all right, you have these sodium channels, and then you have these voltage-gated sodium channels. So sodium's on the outside. These channels have to open. That's what the SA node is going to cause. And why they happen, no one really knows, but that happens and such. And when they open, the sodium rushes from high concentration to low concentration. It moves in. And when that moves in, the cell's outer membrane goes from, or the inner side of the membrane goes from negative to positive. That's depolarization. And then a few millionths of a seconds later, those sodium channels close. Normally in a skeletal muscle, as the sodium was rushing in, the potassium channels would open and the potassium would flow out. Not so in a heart muscle. The sodium rushes in a heart muscle, you depolarize, and then you have on the same membrane of the heart muscle cell, you have calcium channels, and they open. And so calcium will go and move into the heart cell from this extracellular fluid, this ECF, and such, and also from the sarcoplasmic reticulum of the heart muscle itself. While that's happening, while this calcium is flowing in, potassium stays in. You know, the calcium the channels are open, but the potassium can't cross. You know, so it stays depolarized. The muscle cell, the cardiac muscle cells, stays depolarized a much longer time than a normal skeletal muscle. All right. So while that's happening, that's known as the plateau event. Then the potassium channels open, and then potassium flows from high concentration to low concentration, and then that repolarizes the membrane, and that stops the contraction. As all this is taking place, that sodium-potassium pump constantly runs, constantly is working to put the sodium and potassium back in its place. When it repolarizes, the calcium channels close, calcium pumps run, they're constantly running, and they bring the calcium back out, and then that stops the contraction. So the potassium has to leave to trigger this event. The calcium has to be cut off, and then the calcium pumps very quickly remove the calcium, and then the contraction ends. The heart is very susceptible to potassium. You need to maintain a gradient, and if there's a lot of potassium in the blood or in the extracellular fluid around the heart or in the heart, around the heart muscles themselves, the potassium won't leave. And if the potassium doesn't leave, the calcium stays bound, the muscle stays contracted, the heart stops. So when everything closes, when everything depolarizes, when everything happens like it's supposed to, you do have that refractory period where the muscle itself can't be stimulated to contract again. This is a prolonged time in cardiac muscles to prevent tetanus, to prevent a Charlie horse. You really don't want a Charlie horse in your heart. It would be bad. So, there you go.